So last time we almost finished discussing the normal distribution. And we looked at this function. The most important thing about this function is that what is its shape. So it's quantifying probabilities for you for a variable x, and this is how it looks. So the probability is evenly distributed. For this one, it's centered around x is equal to 0. That's also its mean and also the most probable value of x, where there's most highest value of this function. And there is a certain width of this probability, which is this sigma. So this thing over here, that is the standard deviation. While this guy is here for normalization, so that the total probability is 1. Then what we can do is make it centered around any other value. All you have to do is shift the value of x. So right now it's centered at 0. If I replace this x by x minus some value mu, so that x minus mu becomes a new variable, let's say y. This graph, if I draw this graph, it's exactly the same graph, same width, whatever I put here, this is still having the same standard deviation. Exactly the same shape, everything is same, except that instead of at x is equal to 0, now its central position is x is equal to mu. So for this function, the mean value of x, which is we have been denoting like this, would be mu, while standard deviation of x would be sigma. So this kind of, now this function is the most generalized form of the normal distribution. That means the distribution is completely specified by giving only two things. One is it's this number mu, which is its mean value, telling where it's centered, and also giving its standard deviation, that how broad it is. You can change this number and make it broader, or make it this number smaller, and that will make it sharper. And you can take these shapes and put them anywhere you like, giving it any value mu. This is mu1, this is mu2. But once you give the mean value and the standard deviation, everything else is set because it's the same function. You cannot change this function. Only this form of the function is the normal distribution, and the only free variables available to you are this mu and this sigma. So that means this probability distribution is specified once you give the standard deviation and its mean, and all other probabilities Any kind of question you want to ask about the probabilities of this variable x, you know what the answer is. The answer will be computed using this distribution over here. So suppose you want to compute, first of all, how will you compute probabilities using the normal distribution? Let me put another notation which is used in the book. So this function, which I am writing like this, is a function of this variable x. It's a normal function specified by sigma and the mu. This in book is just denoted by n. And you know it's a function of some variable x. And you just give its mean value and its standard deviation. So whenever you see this n mu sigma, you know that you're talking about a normal distribution whose mean is mu and whose standard deviation is sigma. Now, how will you compute the probabilities? So suppose you're given some n mu sigma, and this is its graph. Here is the mu, and the graph looks like this. You want to ask what is the probability that x, whatever your variable is less than a number b. So there's some value here, x is equal to b. What is the probability that you will get the value of x as less than b? That means you are counting any value which x takes less than b is your acceptable answer. So clearly it would be all this area as per our previous discussion. So it would be minus infinity to a n of mu sigma dx. On the other hand, if you want to ask the question that what is the probability that x is between a and b, so this is b. Let me draw it again. So you have a value x is equal to b and another value x is equal to a. So you are counting all those values in this interval. So that would be all this area, which is under this curve, but lying between x is equal to a and x is equal to b. So it would just be from, well, this was b. Sigma d mu. Now, how will you compute this integral? You can do it using a computer, and if you just put in Google normal distribution computation, you will get lots of websites which can do it for you. And you can do it using some charts. There's a chart given in the book. You can use that to compute these. And the standard way to do, one of the ways to do it is by first invoking the standard normal. So what is the standard normal? The standard normal is a normal whose mean is 0 and whose standard deviation is exactly 1. And it's also given this symbol z. So its standard deviation is 1. So in its normalization factor, you have only 1 over under root 2 pi. And this function just becomes the variable I'm writing as z square and 2 divided by 2 because sigma is 1. So it's some normal which is centered at 0, and it has a standard deviation which is exactly equal to 1. Now you can map the probabilities of any normal to the probabilities coming from the standard normal. All you have to do is do a change of variable. So you can map probabilities of any normal, that means having any mean and any standard deviation, to probabilities coming from the standard normal. So how does this work? Now suppose you are given a normal, you're given a variable, you have a variable, a random variable x, and its probabilities you want to know, and you know that its distribution is normal with this mean mu and standard deviation sigma. You want to compute this probability that x, this is the most general thing you can do for a continuous variable, probabilities between two numbers, that x occurring between two numbers a and b. And this we know is just this integral this is the distribution, you integrate it between the limits a and b, and that gives you the probability of it being x is equal to a and x is equal to b. But this same integral I can compute by doing a little bit of change of variable. So define a new variable z by x minus mu over sigma. So what does this mean? This means that z sigma plus mu is equal to x. And from here, I have that dz times sigma, when I take the differential on both sides, this is a constant, so this goes away, is dx. So I can replace this over here and replace this over here. Also, when x is equal to a, because I want to know what is the probability of x between a and b, but when x is equal to a, z according to this formula is at a minus mu over sigma, some other number, not number a, some other number which you can compute by doing this. Let's call it ZA, this number. And when x is equal to b, then it is obviously just this. And I can also write x minus mu from this, from here, is z sigma. So when I replace all this, I'm writing this original formula for probabilities, that x is between a and b. That integral changes. I can write the same integral by using this substitution. This was the integral. It becomes zb e minus z square over 2, because x minus mu becomes z sigma. So when I square it, I get z square sigma square, and sigma square cancels with the sigma square. So I get z square over 2 dz. This is nothing except the probability of this other variable z to be between za and zb, where this variable z, its probability distribution is given by this. And I had a z here, sigma here, dx was dz sigma. So that sigma cancels with the sigma square over there. So it is exactly this. So now if you look at this guy, this is just the probability distribution, which is normal, but of a variable z whose mean is 0, because nothing is being subtracted from this variable z. And 2 is multiplied by 1, and 2 pi is multiplied by 1. That means it's a normalized probability with a standard deviation equal to 1. So this probability, original probability, is equal to the probability of this new variable z to be between za and zb, where z is distributed according to standard normal distribution. So that means any probability for any normal I have to compute, I can do it in terms of the standard normal, probabilities for the standard normal. And in fact, this is given when I compute this. So suppose you want to compute for the standard normal. The probability of z being less than a number, let's say b, is just going to be minus infinity to b This is given a name f of b, and you can call it the cumulative distribution, cumulative standard normal distribution. So what is it is telling you? It is telling you the probability of this standard normal variable z being less than b. You draw the standard normal, take your desired b, and this area is just this integral. So these numbers are given in tables, or you can look up and find them on Google, compute them on Google, and they will, you can then put all your answers in terms of, in terms of this cumulative standard distribution of the standard normal. Aliza, and I'll come to you in a moment. Suppose if you want to find the probability of Z being between A and B. So Z greater than A less than B. That you can write like this. Here's your standard normal. And here's B. Here is A. So you need this area. But you can compute this area by first computing the total area under this curve up to B and subtracting from it this area up to A. But area up to B, that is the total probability, that is just equal to this thing, which we just wrote above, f of B. The cumulative probability of Z being less than B. And from it, you want to subtract the probability of Z being less than A, because you want to subtract this area. So it would be just this. So even this kind of answer, you can compute in terms of this cumulative distribution. All you have to do is subtract two numbers. So there was a question by Alizan.
Sir, in ITF we studied like B minus mean upon standard deviation would give us something called Z, and then Z का हमें table दिया होता था, हम उससे probability निकाल लेते थे. So basically this is the same thing, right?
This is the same thing. This is, you can look up this table. It's given in the appendix.
So ये आपने सिर्फ table का formula दिया, right? We can literally look up the table and we can write the answer.
Yeah.
Thank you, sir.
So let's for example, I can ask this question. So you are given a variable X. Its distribution is mu sigma. And you want to ask what is the probability that X is within one standard deviation. This is one X probability of X being within one standard deviation. So it tells you something about what this standard deviation means in terms of number, how much it covers. If you say that standard deviation is a measure of how far away from the mean you expect the variable to be found, by what probability you expect it to be found within this range. This is the range of standard deviation. So what you can do again is compute this variable. Now, यहाँ पे when X is equal to sigma, Z is equal to 1. And when X is equal to minus sigma, Z is equal to minus 1. So it's saying the same thing, that the answer of X being between its standard deviation would be same as Z being between its standard deviation. So all these normal curves, they give you same answers if you translate the standard deviations. Like whatever the answer is for one particular normal, within one standard deviation would be same as any other normal. So you can just compute this guy, and that will give you the answer. Now this thing you can compute in many ways. I'm going to tell you a few ways. So this probability, how to compute this. One method is, how do I change the share? So you can go to, for example, this Wolfram Alpha website if you really wanted to compute the integral. And over here, this is just for an example. You don't really need to do it. I just wanted to show you that this integral really is this. And I can write this formula. So it gives you a syntax how to write this integral. It says integrate 1 over square root 2 pi exponent of minus x squared over 2. So that's the standard normal, which you're integrating from x is equal to minus 1 to 1. And it gives you an answer equal to 0.68. That means you have a 68% chance of being within one standard deviation. Let's see what happens if we change it to 2 standard deviation. Again, 2 standard deviation of any normal distribution will be, that probability will be equal to the 2 standard deviation of the standard normal, which I am doing over here. And when we do this, you get 95% chance that you will be within 2 standard deviation. When we go beyond that, things become almost 0. Well, almost 1. So within 3 standard deviation, you are covering like almost, you can see this normal distribution over here as well. You're covering all this area. So only very little is left out. You're covering 99.73% of the area. So you're getting almost 1 probability, and anything beyond that is ridiculously small. So this is 99.9999. So what it shows, let me write here, that within 1 standard deviation, the probability is 0.68. Within 2 standard deviations, probability is 0.95. And anything beyond this is practically 1. Or something like that. And if you want to ask the question that x is not between, let's say, probability that x is outside 2 standard deviations, that would be just 1 minus this probability. So it's 1 minus 0.95, only 5% chance that you will land outside the 2 standard deviations. Now, let's look at the use of this function to an example. So suppose a large organization This is slight change on the example given in the book. A large organization, they give out annual increments, and they have decided that they will give a mean increment of 12.2%, and with a standard deviation of 3.6, and it is known that the increments are distributed normally. That means they are given by a normal distribution. So if you pick a person from all these people in the organization, what is the probability that the increment will be more than 15%? So probability that increment, which I'm denoting as x, is more than 15. You have this x, mu is 12.2, and it's distributed something like this. Somewhere here is 15, and you want to know that what is the probability that if you pick a person, the increment will be more than 15%. So that means you want to count all this area. All this area beyond 15. So the way you can do it is, one way to do it is you compute this standard normal variable, and you want to compute this probability that z is, if I compute this probability that z is less than 15. I want to compute this area, but the way I can go about is first I compute this, and then my required probability would be just so I'm creating a standard normal.
सर सर इसके अंदर z लेस देन 15 होगा, या जो हम z स्कोर निकालेंगे वो वाली वैल्यू आएगी?
Sorry, x less than 15. So I construct a standard normal, and I want to just know that what is this value z, which corresponds to the 15 for the variable x. So it would be just 15 minus 12.2 over sigma, which is 3.6. So this gives me 15 minus 12.2 divided by 3.6. So this gives me 0.7777. I should, if I want answers in probabilities accurate to 2 decimal places, I should at least keep up to 3 decimals in this. Sorry, this is not probability, this is z. I should keep it up to 3 decimal places. Now you want to compute this function, which is just the probability of this z variable being less than 0.777. So you can do it by looking up in the table given in the book, or much easier, you can go to, for example, this website. If you just put in, because this is the cumulative normal distribution, you go to so if you put in Google normal distribution calculator, you get many websites. For example, this one, StarTrek.com, it has this normal distribution calculator. Over here, you put the standard value of Z, and if you calculate, it gives you the cumulative probability, which is 0.781. So the required probability would be, let me just share the screen, that would be easier. So the required probability would be 1 minus 0.78, which is equal to 0.22. So you have a 22% chance that if you pick a person at random, they will have an increment greater than 15%. By the way, this going into the standard normal is most useful if you are working with a table. Let me probably show you this table as well. If you go to index tables, yeah. So they are all listed over here. You can read up the value of Z, and you can look up the value here. So like 0.77 gives you this, but I had a better accuracy. It gives you 0.7794 over here. In my computation, I had kept the up to 2 decimal places. Here you pick 0.07 and add to it this 0.07, which gives you a 0.77, and it picks up this number 0.7794. We had 0.781 because we did a slightly more accurate computation, because in that website we put in 3 numbers and it did a slightly more accurate computation. But the table gives us 0.77, pretty close to this one. If you're looking up in this website, or if, for example, in SPSS, which I will show you next time, then you don't really need to go to the standard normal most of the times, because what you could have done, directly worked with your regular variable, and we were looking for probability of this being greater than 8, and our normal had a mean of 12.2 and the standard deviation of 3.6. So you can directly compute it, and it still gives you the same answer, 0.78. So you can do it directly. You don't really need to go into this, but since it's used so many times in the book and in literature, so it's necessary to know that what is the standard normal and how to go from any other normal to the standard normal in computing the probabilities. Now, suppose if I ask another question, that what is the probability that they have an increment that a randomly picked person has increment between 15 and 16%. Then you need this guy. In other words, you have to compute this Z. So let's say this is ZB and ZA was this one. You have to compute ZB for this 16 one, which is 16 minus 12.2 over 3.6. So it gives you 16 minus 12.2 divided by 3.6. So this is equal to 1.055. And now you compute this function 1.055. You can do it from this table. 1.05, it will only go up to this accuracy, which is 0.853. Or you can do it from this website. I had computed 1.055 for the normal random variable. Mean, I'm doing it for the standard one, so I put a mean equal to 0, standard deviation equal to 1, and it computes the cumulative probability. It's 0.854, which is close to what I looked up in the table. Now, this probability is then equal to the probability of it being up to 16 minus the probability of it being up to 15. So it's just 0.854 minus this number. .78. That's the answer. I don't need to even go into this 0.22 because I have a 15 here whose area I had computed was 0.78, and I have a 16 here. Whose area I just computed. So the difference of these two areas give me my desired area here. So I just take the difference of these two numbers, and that gives me the required probability, which is around 0.065. So 6.5% chance of it being between 15 and 16. Now let me address another issue which was raised, that what's the relation of these discrete using this probability distribution for continuous variable for the discrete variables. How do I use it to describe probabilities for discrete variables? So suppose you knew that the salary increments, it is known that salary increments are given in increments in sizes increasing by in figures in percentages increasing by 0.2. So you can have a number like 13.8, 13, then 14, then 14.2, 14.4, and nothing in between. So these are like discrete steps. But I can still say that this normal distribution approximates whatever the discrete distribution is. My normal distribution approximates it very well. Now I can ask the question, because now since a discrete variable, I can ask what is the probability that a person gets an increment of, let's say, 14.4. How do I answer this question? Well, I can make a bin. Make a bin which has only, make bins, so there are two rules. Make bins of equal sizes and pick a bin that has only 14.4 in it. That means I will have to make a bin between 14.3 and 14.5. So I can compute this function, this cumulative function for z coming from 14.5 minus, what was the mean? 12.2 over 3.6 minus this cumulative distribution, and this will give me the required probability of the increment exactly being 14.4. Or I could probably use this one, this example which we had done before. So let me choose this bin, 15.1. So this is the probability that x is equal to x is equal to 15. Assuming that these increments are now discrete variables, the change inside by an addition of 0.2. So again, you can go to that website and I can do this thing directly instead of going to the normalized thing. So 12.2 was the mean and standard deviation was 3.6. And here you can now, since you have chosen the mean and standard deviation of the original distribution, so you can directly put in the values for the original distribution. 15.1, it gives you 0.79, and from this I subtract the number for 0.773. So it's 0.02. And you can see that it's much less than the probability of salaries being above 15, because it's like exactly being exactly 15. Now, sticking to this example, let's do something more. And now we are invoking our central limit theorem.
So can you scroll up a bit?
Wait.
Okay, thank you.
Now this theorem, it has, let me just write it again. It has, I can divide it into two parts. That if you pick a sample, from a population that is normally distributed, then the sample mean will also be normally distributed, approximately. Because in the end, it is a discrete variable, so we are only talking about approximately normally distributed. With same mean, with same expectation. So this is what we know. That whatever is the population mean will become the mean of the sample mean, the expectation value of the sample mean. And the standard deviation of the sample mean will be much less than the standard deviation of the original population. Actually, you know that by what factor, where this is the size of sample. Over here, this part is important, that the population is normally distributed, which applies to this our case. The second part is even more interesting, that everything goes through, same holds true, even if population is not normally distributed, is not normally distributed, no matter what the distribution is. Your sample mean will still be normally distributed if sample size is big enough. Well, you can ask how big. Practically speaking, for any population distribution, it depends on how skewed, how weird the population distribution is. But for most population distribution, practically speaking, any sample size around 25, its mean already becomes very good normal distribution. For most cases, even sample sizes of 5 or 6, they start giving you normal distribution. But at 25, it's almost guaranteed. And at 50, like you will be very hard pressed to find an original distribution which will not give you a sample distribution, a sample mean whose distribution is not normal. So for a large enough, and practically speaking, for any n around 25, you can assume that its mean, the distribution of its sample mean will be normal. But we are in this situation because our original sample is normally distributed, and now we pick 9 persons. You pick 9 people from the employees population. What would be the probability that mean of their increment is greater than, let's say, any value? What is the probability that mean of the increments of people in this sample? So you randomly picked 9 people and you noted down the increments and you computed their mean is greater than, let's say again, that 15%. Obviously, intuitively, you expect that it would be a much smaller probability because you would be picking people from anywhere in this distribution, some here, some here, some here, some here. So the mean you will compute will tend to be clustered around, more clustered around the central value. But how can you answer this? Well, you know that what would be the standard deviation of this. You know that x bar, which is the mean of the sample, will be normally distributed because the original population is normal, and its standard deviation would be 3.6 over under root of the sample size, which is 9, and its mean of its own normal curve would still be same as the original one.
Sir, how did you get 3.6?
Because I'm using the same population. It's the same problem. It's the continuation of same problem. We were given that in this company, everyone, if I count the increments of everyone, their average is 13 point. No, sorry, not 13. It was 12.2. No, sorry. Yeah, its standard deviation was 3.6. This was given to me. That is, mean is 13, mean is 12.2, and standard deviation is 3.6. This was given to me. Now I know that if I pick a sample of size 9, their mean will be distributed normally. Now this is the distribution of the means of the samples. They will still be distributed around 12.2, but their standard deviation would be given by this number. So if I want, that's the theorem. This is the theorem.
Okay.
So this theorem will be used again and again. If you pick a sample, the sample mean is also normally distributed, but its standard deviation gets reduced. So this probability that the mean is greater than 15. Because it's a normal distribution, so you can compute this z variable. -15 minus 12.2 over this new 1.2. It would be actually 1 minus this thing, where this is the standard normal. So we can go over here, do it in many fashions. For example, I can directly do it by asking that I want the answer to be bigger than up to 15, and mean is again going to be same, but standard deviation is now 1.2. So it's 0.99.
Sir, how did you get 15?
Because I didn't even do this. I didn't go to the standard normal. I just directly did it over there. Because this cumulative distribution function in this calculator and in most of the calculators, like I'll show you the SPSS calculator next time, you don't even have to go to the standard normal. You can directly put in the mean of your distribution, which I know from here is going to be 12.2. And you can put in the standard deviation of your normal, which is 1.2 directly. And then you can compute the cumulative probability that your variable is less than a certain number. So in our case, we are looking for 15. So I put that here and I calculate. If you want to do it in the standard, using the standard normal, then I have to put 0 here, 1 here. But here I have to compute the number for 15 using this. So z would be 15 minus 12.2 over 1.2, which comes out to be, let me do it on the calculator. -12.2 divided by 1.2. 2.33. So if you want, you can look it up in this table. 2.33, so it's 0.99. That's what I found before. Or you can put in here 2.33, 0.99. The standard deviation changed because I'm answering a different question. The question is that you had this population where the increments were distributed around 12.2 mean with a standard deviation of 3.6. From this population, I picked up 9 people. And I computed the mean of those 9 people, and I'm asking, what is the probability now that this mean is more than 15? So that distribution has a different shape. Its standard deviation is given by this formula. Now let's do another example. So suppose you have these spark plugs for cars made by a certain company, and they provide you this specification that our mean life of these plugs is 60,000 kilometers with a standard deviation of 4,000. So mean life, I should say, their life is normally distributed. And this is what they tell you, that the mean life of our plugs is 60,000. The lives are normally distributed, and the standard deviation is 4,000. You want to check their claim, that is it really true? You're not gonna check on all the plugs. You cannot check every plug in the made by the company. You pick a sample of 100 plugs. Now you know that if I just check their lives and compute the mean, what is the probability that it is 3 sigmas away from its normal distribution? We just found out that this is like having a standard normal and having 3 sigmas. This probability is is about 0.001. So very little chance that this will happen. But what is 3 sigma in this case? You know that sigma of x mean is whatever the company claimed is the standard deviation of the spark plugs divided by the under root of the sample size. So it's 4,400. So what does that mean? That means that if your mean for these spark plugs comes out to be 60,000 minus 400, you would say like, well, there was a chance that this happened because this can happen in 33% of the chance. But if it was 3 times this sigma, 3 sigma away, so which is equal to 58,800. So if the mean life of this sample of 100 is 58,000, then you already suspect that there was a very, very little chance, almost impossible, only 0.1% chance that this would happen. Then either the company's mean of its original population is different or the standard deviation is different. So what they are telling us is wrong. We are very confident that it is wrong. And we did it only by selecting a sample of size 100. So any question about this one?
So ये last part समझ नहीं आया.
I didn't take any 25 over here. Why this question? Okay, so I was given that ये इनकी mean life है, population की, company का claim है, and the standard deviation is this much. I pick a sample of 100 and I make their mean. I know that if I plot the means, I'm not making many means, I'm only picking one mean, but I know that there's a probability distribution of these means, which is centered around 60,000. This is the probability distribution. And I also know what's the width of this probability distribution. What is the sigma of it? It is 400, because that's how it should be, according to the formula and according to this central limit theorem. So that means if I pick a sample of 10 and compute the x bar, it would be somewhere here, here, or here, or here, somewhere here. But if I get a number here, whose probability is very, very little, then I would start suspecting that how could it happen that I got such a low number. And all I'm saying is that if I get this number, I should be suspicious, because this number is 3 sigma away from the central value of this normal distribution. And 3 sigma away means that the probability is extremely low. We just saw it at the beginning of the lecture. You can compute it. All you are doing is computing the probability, this probability of z being less than -3, because you compute this z by, this is the central value. So when you're doing by 3 sigmas, this is how your z is distributed. And at 1 minus 1, you have 1 sigma. And here you have 2 sigmas. And 3 sigmas is here. So this number, when you compute, is extremely small. You can do it over here. -3. It's 0.001 is the probability that you are below the 3 sigma. And I can do it this way. Standard deviation was only 400, and I was 58. It's 0.001 is the probability, so 0.1% chance. So this gives you an idea, this formula for standard deviation. The formula is, this is the standard deviation of the population divided by the sample size, square root of the sample size. It gives you the idea, can you even get this number when you make a mean? So I'll stop here and I'll upload some more examples of it. I'll upload it,
sir.
because wait, let me complete my sentence. I'll upload some more examples because I want to move forward. So I think I'll give you some more examples in a tutorial so that you can get some more practice and try to move forward in the next lecture. And I'll also, in the example, I'll also explain how to use SPSS. If you don't have SPSS, you can just download PSPP. I'll send the link for it. It's free and it works exactly the same way. But for what we are doing, you don't even need it. You can just I'll send the link for this calculator, and you can do these computations on this online calculator. There are many online calculators available. Yeah, what's the question?
Sir, this 400 was basically sample size, right? This is basically sample
No,
standard
it's not
deviation.
the sample size.
No,
4,000
sample standard deviation.
the sample standard deviation. You shouldn't call it
100
sample
is a
standard
sample.
deviation. It's not the sample standard deviation. It's the standard deviation of the sample mean. Sample mean is a random number. It's the standard deviation of that. It's the expectation of where would you find this standard deviation? Or where would you find this sample mean? Standard deviation of the sample is different. Sample में आपके पास 100 numbers हैं. They would be spread in a certain way. उनकी कोई अपनी standard deviation होगी. We are not talking about that. We are taking all those numbers and making a mean out of it. And asking where could that mean be? So our theorem says that it would be around the mean of the whole population, and it would be distributed according to